Swayam Prabha. Digital India. Educated India.
Let us continue our discussions on relative motion in rotating frames. In the last lecture also we just started kinematics in rotating frames. Here we are going to look at problems and discuss further. Just to recapitulate what we discussed, in a rotating frame which is the small xyz represented by the green frame in the figure, which is rotating at an angular velocity omega vector, and it has an angular acceleration represented by that alpha vector, and capital XYZ is a fixed frame, fixed with respect to distant stars. Always remember that this omega and alpha are always as seen by the inertial observer, because as we have seen the local observer B cannot see the rotation. Now, the position relation R A is R B, position vector of A R A is equal to position vector of B, which is R B, plus that relative vector R. We had differentiated this and obtained the velocity of A in terms of velocity of B, and the relative velocity. Remember, relative velocity is the velocity seen by the observer B of the point A measured in his or her coordinate axis, and omega cross r is the frame derivative because of the rotation of the coordinate frame small x y z. And we had differentiated, time derivated the velocity vector to find out the acceleration vector. The first term, so d dt of V A is acceleration of A, d dt of V B is acceleration of the observer B. Then this V rel, the total time derivative as seen by an inertial observer is given by this prescription, del V rel del t plus omega cross V rel. And similarly for omega cross r, which is the frame derivative vector, we have the same prescription. Only thing, d omega dt is alpha as in the inertial observer, as measured by the inertial observer cross r, and then omega cross d dt of r is del r del t plus omega cross r, same prescription. This is the rate of change of r vector as seen by the inertial observer. We had rearranged the whole thing and obtained this master equation for acceleration of A. In terms of acceleration of B, A rel, alpha cross r, omega cross r, and 2 omega cross V rel, and these are the names. Local, this is the local acceleration, remember, is the acceleration measured by this observer B sitting in a rotating frame and measuring and observing this particle or point A moving in his or her frame. Similarly, V rel. Okay, alpha cross r is the tangential acceleration, centripetal acceleration is omega cross r, and Coriolis is 2 omega cross V rel. Now, let us look at some special cases of these general formulae that we have derived. Suppose A and B are 2 points fixed on a rigid body. What happens to our these general expressions? The general expressions are, remember, these are our general expression. This is the velocity relation and this is the acceleration relation. So, these are our general relation. Now, let us specialize to certain situations. The first situation that we are going to consider is when A and B are 2 points fixed on a rigid body. If that be so, let us write down the most general velocity relation. So, velocity of B is velocity of A plus V rel plus omega cross A B, the general velocity relation, of which Now you see, because both A and B are fixed on the rigid body, just like you and another person both are sitting in the same auditorium, you are sitting in the auditorium, you are not moving. So, you are fixed on the earth, then VREL is 0. You will never measure, you will say that VREL is 0, because that the vector from you to that person is not changing, neither in direction nor in magnitude. Therefore, VREL is 0. What remains is because of the rotation of the earth, which is omega cross AB, omega of the earth cross AB in this particular example. Here it is the omega of the body cross AB. Therefore, this velocity relation simplifies, VB is VA plus omega cross AB. Let us look at the acceleration expression. The master equation is written first, then I see that because A and B are fixed on the rigid body, therefore, if you ask the person A what is the acceleration you measure of person B, 0, just like two persons sitting, you are sitting and another person sitting in the auditorium, if you are asked the acceleration of that person, you will say 0, both of you are fixed to the earth. But the other vectors, because of the change of the direction, because of the rotation of the earth, you have change in the direction of the vector that joins you and that person. So, alpha cross AB, omega cross AB, and 2 omega cross VREL, again VREL is 0. So, that term also drops out. Therefore, for 2 points on the rigid body, the acceleration expression or relation also simplifies. If that point B is like a pin or another person walking on a straight path, you are A sitting on a chair and that person B is walking on a straight path. VREL is the velocity that you measure, velocity of that person as he or she walks on the straight path, and AREL is the acceleration that you measure of the person when he or she walks on that straight path. Then there is no simplification, the whole expression is required. You have VREL and of course, omega cross AB, the body is rotating at angular velocity omega. Similarly, acceleration, everything is present, all the terms are present, angular velocity, angular acceleration, and and all those effects because of VREL and AREL. So, all the terms are present. Now, B is moving on a curved path of a certain radius of curvature, here I have called it rho, and because of the curved path, B will now have this AREL of B has two components, the tangential relative acceleration and the normal relative acceleration, normal to the path. This normal relative acceleration is because of the path curvature, tangential exists even for a straight path. Again, there is no simplification in velocity relation, but a little complication in the acceleration relation. You have to remember that AREL is composed of two parts, AREL tangential and AREL normal. Normal is because of the path curvature, which is VREL square by the radius of curvature. So, AREL tangential is tangential to the path. So, this is the rate of change of essentially rate of change of VREL, and because of the path curvature there is an AREL normal, which is VREL square by radius of curvature of the path at that instant. So, VREL dot VREL by rho, if you want to write in vector notation. So, that is the magnitude, and the direction will be in the direction of the center of curvature of the path. So, this is the expression. Let us understand with some examples now. In this problem, which is taken from the book of Merriam and Craig, this says just as an airplane is taking off, a person A, I will mark out, the person A is here, this is person A, is walking forward in the central aisle with velocity dl dt, L is marked out in this figure, and acceleration d2L dt2 relative to the cabin. These are very easy to measure in the cabin. So, that is specified. Derive the absolute velocity and acceleration of the person as seen by a ground fixed observer if the point C on the wheel assembly has velocity Vc. You can find C at the center of the wheel assembly, that red dot at the center of the wheel assembly, that is C. So, the point C on the wheel assembly has velocity Vc, acceleration AC both in the forward horizontal direction, and pitch angle theta marked here is increasing with angular velocity omega. So, d theta dt, and angular acceleration alpha, which is d omega dt. So, everything is there, all rates are present. We have to find out the absolute velocity and acceleration of the person as seen by an inertial observer. Whenever we say absolute velocity, absolute position, it means as seen by an inertial observer. We will use the xy frame that is given in the figure. I have written out all the given parameters that are specified in the problem. We have to find out V A and A of A, acceleration of A, velocity of A and acceleration of the person A as seen by an inertial observer. We have to represent, so when we are going to use this xy frame, we have to represent all vectors, all relevant vectors in this xy frame. For example, this Vc, the velocity of this point C in the wheel assembly, which is actually horizontal, but it has to be represented in the xy frame, and this is the representation of Vc in the xy frame. Vc is the magnitude, this is the magnitude, and cos theta I cap minus sin theta j cap is the direction, unit vector direction. Similarly, acceleration of C AC magnitude times unit vector direction, which is cos theta I cap minus sin theta j cap. VREL, what is VREL? VREL is the velocity as seen by an observer sitting, that B, you can see here B is the origin of the frame xy. VREL is the velocity of that person A as measured by the observer B inside the aircraft. So, that is the idea of VREL in the rotating frame. Similarly, AREL is L double dot I cap. So, VREL vector is L dot I cap and AREL is L double dot I cap. Omega angular velocity, everything is specified, it is in terms of k cap. So, omega k cap, alpha is also alpha k cap, which is d omega dt, and omega is d theta dt. Now, VA is Vc plus VREL plus omega cross Ca. I have written the full expression. Now, I will plug in the values. Vc is known, VREL is L dot I cap, and omega cross Ca, omega is omega k cap, and Ca vector, Ca means from the center of that wheel assembly to A, which is, you can see here that this height is measured, is specified h, and this distance is L, therefore, L I cap plus I h j cap, L I cap dot plus h j cap. That is the vector Ca. So, Ca is Cb plus Ba. So, that is how we arrive at this. Just take the cross multiplication and cross product and then rearrange, you are going to get this expression, straightforward algebra. Next, we move to the acceleration. This is the master equation. AREL, because the person is walking in a straight path, has only one component, it is along the x axis, and that is what we have written out, L double dot I cap. Just plug in all these expressions and simplify, and that is going to be the expression of acceleration of the person A as seen by an inertial observer. So, I will leave it to you to check out the details. Let us now move on to this example of a rolling wheel. A wheel of radius r is rolling on flat horizontal ground. C is the point of contact, and I am assuming that this wheel is rolling without slipping. Now, I express the velocity of point C in terms of velocity of point O, which is the origin of the frame x y. This frame x y I am considering as a translating frame. The origin of the frame is sitting at O, the center of the wheel, the geometrical center of the wheel, and x is always horizontal. This is a non-rotating frame. I am trying to express the velocity of point C in this non-rotating frame with respect to the center of the wheel. So, Vc is Vo plus Vrel plus omega cross Oc. Now, notice that C is a point which belongs to the wheel, but currently in contact with the ground. C is not a point on the ground, C is a point belonging to the wheel, but right now is in contact with the ground. So, it is a contacting point. Therefore, C is a point belonging to a rigid body, O is a point belonging to a rigid body, both are points on the rigid body, same rigid body. Therefore, Vrel is 0, we have discussed this, but because the body is rotating, now you see I am representing in a non-rotating frame, but these expressions will remain omega cross OC, because that is the rate of change of that vector OC. If you think about it, OC is a vector fixed to the rotating wheel, because C is on the rotating wheel, point on the rigid body, O is a point on the rigid body. Therefore, as the wheel rotates, frame is not rotating, but the vector is rotating, and that must be accounted for. So, that omega cross OC is because of that. Now, I can use this xy frame to represent everything. If you do that, now what I have written is, you see the x is in the direction of motion, therefore, the velocity of the wheel is like this, it is moving in this direction. Omega, this I am representing as minus omega k cap is a vector now coming out of the plane of the screen. Therefore, this expression is the representation of omega vector is minus omega k cap, cross OC is minus r j cap, it is minus r j cap, this is OC, and magnitude is r and direction is minus j cap. Therefore, V of point O is omega r I cap, just take the cross multiplication cross product, you will get this. Now, because this is a non-rotating frame, I cap is not rotating, I can derivate this and find out the acceleration of O. It is the coordinate derivative of which r is not changing, radius of the wheel is not changing, omega can change of course, omega dot is alpha, and I cap is not changing, therefore, acceleration of point O is simply alpha r I cap. Now, acceleration of the point C, I would like to find out the acceleration of point C. Please note here this C is missing. So, acceleration of this point C, this is an interesting calculation, we would like to find out whether C has an acceleration or not. Here you see V velocity, because C is a point which is of the wheel currently in contact with the ground, it does not have any velocity. So, velocity of C is actually 0, and that is how we have used and found out V naught. Vc is 0, velocity of C is 0. Why? Because it is in contact with the ground, ground has 0 velocity, it is not moving, absolute velocity of the ground point is 0. Therefore, Vc is 0, that is equal to V naught plus Vrel, which is 0 plus omega cross OC, and because this must be 0, therefore V naught must be equal to minus omega cross OC, and that is how we have arrived at these expressions, minus omega cross OC. And so, this minus and omega itself has this representation and OC has this representation, and from there we arrived at V naught of, so velocity of the center of the wheel, and by differentiating we get acceleration of the center of the wheel. Now, we are interested in finding out the acceleration of the point C, that I write in terms of acceleration of point O, which I have derived here. Acceleration of O, A rel is 0. Why? Because O and C are points on the same rigid body. A and C are points on the same rigid body, therefore, A rel is 0, plus alpha cross OC plus omega cross OC, again V rel is 0, therefore, 2 omega cross V rel drops out. Okay. So, this is AC, acceleration of AC. I have plugged in the various expressions, and if I do this calculation, finally you see this first term is alpha r I cap. Now, here this also generates minus alpha r I cap, as you can check easily. Therefore, these two terms cancel out. What we are left with is acceleration of point C is omega square r j cap, which means the point C has an acceleration which is vertically upwards. Its velocity is 0, but at this instant the acceleration, C has an acceleration is vertically upwards, its magnitude is omega square r. The magnitude of this acceleration of the ground contact point is omega square r, and it is vertically upwards. Now, following this, I mean, you can extend this to study acceleration or velocity of various other points on the wheel. For example, velocity of A is velocity of O, which is known, we just now derived, plus omega cross OA, and it can also be written in terms of velocity of point C, velocity of C plus omega cross CA. Now, you should note V rel in all these expressions, in all these relations, V rel is 0. I am not writing it anymore, because these are all points on the same rigid body. I have not written it, but you can understand. So, V rel is 0 in all these expressions. Therefore, I can express V A, velocity of A, in two ways, in terms of velocity of O and in terms of velocity of C. Both ways I will get the same result, but this gives a good geometric picture. The second expression gives a good geometric picture. If you join, because velocity of C is 0, it is in contact with the ground, if you join C A, then velocity of A is omega cross C A, which means it is perpendicular to C A. Omega cross C A generates a vector which is perpendicular to both omega and C A. What is important here is it is perpendicular to C A. Therefore, the velocity of A can be very easily depicted in this figure if you use that contact point C. It is perpendicular to this line joining the contact point to the point whose velocity you want to represent. Acceleration of A, again in terms of acceleration of C, you can find out, you already know that acceleration of C is omega square r j cap, vertically upwards. If you just plug in these expressions, you will get the acceleration of A, which I will leave it to you to figure out. Let us extend this problem. Here the wheel is rolling on a circular track in a plane, on a circular track in a plane. A wheel rolls on a circular surface without slip. At the bottom position shown, it has an angular velocity omega and angular acceleration alpha, both clockwise, that I have indicated, omega and alpha. Obtain expressions for the acceleration of the ground contacting point C of the wheel and point A at the top, both are marked. So, C is the point on the wheel which is currently in contact with the ground, and A is the topmost point of the wheel at this instant. I take this xy non-rotating xy frame and I will represent everything in this. V c, velocity of point C which is in contact with the ground, so its velocity is absolute velocity is 0 definitely, is V o plus V rel is 0 because O and C are on the same rigid body, plus omega cross O c. This is our expression. We are writing, remember we are writing, we are expressing velocity of C in terms of velocity of O. Therefore, this vector should go from that O point to C. Now, that implies V naught. Now, because V c is 0, so I can very easily take this to the other side, omega cross O c, and finally find out velocity of O, the center of the wheel, is still omega r I cap. Now, this you should also physically understand. This C point is currently the instantaneous center of rotation. Now, the velocity cannot see this curvature of the path. At this instant, C is the center of rotation, therefore, the velocity of the center must be omega r, and that will be in the direction of I cap. But what difference this curved path makes is in acceleration. So, that is what we are going to look at. Now, acceleration of O, the center point, see center point is moving on a curved path. A circular path. And what is the radius of curvature of the path? This capital R is the curvature of the track, and the path of O, the center of the wheel, is this dashed blue curve, that is the path of O, whose radius of curvature is capital R minus the radius of the disc, capital R minus small r, the radius of the disc. So, radius of the path minus radius of the disc, that is the curvature, the radius of curvature of the path of O, the center of the wheel. Therefore, this acceleration of O will have two components, tangential and normal, because of path curvature. Tangential acceleration is same as what we have derived earlier, because you remember that C is the instantaneous center of rotation. Therefore, the tangential acceleration is alpha r I cap, whereas the normal acceleration, which is of course in this direction, normal acceleration, this is centripetal acceleration towards the center B. So, that is the normal acceleration, this is the tangential acceleration. Now, normal acceleration should be tangential velocity of O square by the radius of curvature, and that happens to be omega square r square. Here we have the expression omega square r square by radius of curvature is r minus r, and the direction j cap. This is the magnitude actually, this gives me the magnitude, and so that is the magnitude, and this is the vector. So, direction is j cap That is what I have written here. Therefore, our acceleration of point C is this master equation where A rel and V rel are 0. I am representing in terms of acceleration of O. If I just plug in all these expressions, acceleration of O is known to me, I have just written there alpha cross OC, alpha you can represent minus alpha k cap, OC is minus r j cap. Similarly, the centripetal acceleration, if you do all these things and simplify, it turns out to be a very simple expression given at the end, underlined omega square capital R into small r by capital R minus small r j cap. That is the acceleration of point C belonging to the wheel which is currently in contact with the ground. You can make a few checks. For example, if r tends to capital R if it tends to infinity, that means it becomes straight, then you get back the previous expression. So, this thing you can check. Similarly, you can find out acceleration of the topmost point is acceleration of O plus alpha cross OA plus omega cross OA, and if you do this plug in these expressions, then finally you will get acceleration of point A which is shown here, and you can check. I will leave it to you to check this expression. Finally, we have a problem of this eagle which is swooping down on a mouse moving on the flat ground at a constant velocity Vm. The mouse is moving at a constant velocity Vm, the speed of the eagle Ve, which is also constant, is greater than Vm. This is an assumption and always directed towards the mouse. Calculate the time taken by the eagle to catch the mouse if it starts initially from a height h when the mouse was at a horizontal distance d ahead of the eagle. These distances are all marked out in the figure. In order to solve this problem, we fix the coordinate system on the eagle. I have shown you here, I fix the coordinate system x, y, z on the eagle, and it is fixed to the eagle, which means as the eagle changes direction, this x direction is going to change and hence the y. Capital X is the coordinate of the mouse in this frame along the x axis, and I have also shown the velocity of the eagle Ve and the velocity of the mouse. Now, because this x y is a rotating coordinate system, therefore, our velocity relation, if the eagle wants to relate the velocity of the mouse in its coordinate system, how will it represent? Now, this V mouse is the absolute velocity of the mouse in terms of the absolute velocity of the eagle. So, V mouse is V eagle plus V rel plus omega cross the vector from E to the mouse, which is x vector. I have called this as x vector. So, omega cross the x vector. Therefore, this relation, this is standard kinematic relation which we have derived. So, velocity of the mouse in terms of the velocity of the eagle, and this extra term, for future reference, let me point out this whole term V rel plus omega cross x, this is the relative velocity of the mouse with respect to the eagle. Now, I start representing all these vectors in that x y frame. Velocity of the mouse in the x y frame, so it is the magnitude of the velocity, the Vm, times the unit vector direction. Now, Vm is in the horizontal direction, therefore, and this is the angle theta. Therefore, the unit vector direction in the direction of velocity of the mouse is cosine I cap plus sine j cap. velocity of the eagle, the absolute velocity of the eagle represented in xy frame. Because we have fixed the coordinate system with the eagle, therefore, the absolute velocity of the eagle in the xy frame is along the x axis direction always. So, this is the magnitude V e times the unit vector, which is I cap. V rel, what is V rel? V rel is the velocity of the mouse as seen by an observer fixed in the xy frame, which means the eagle. What will the eagle see? It will see the mouse approaching it only along its x axis direction. Now, x dot, we do not know its magnitude. Therefore, I have taken x dot, this capital X dot I cap, because this V rel as measured by the eagle will always be along its x axis direction, the axis that I have fixed to the eagle. Now, omega, this needs a step. Omega, angular velocity of this frame xy. As you can realize, when the eagle maybe has come here and the mouse has come here, then the frame looks something like this, directed towards the mouse. Therefore, this is rotating like this. If it rotates like this, so I have to represent this vector. Now, theta is measured from the horizontal to this line joining the mouse and the eagle. Therefore, direction of increasing theta, which is, so theta dot is positive in the clockwise sense, but this is in the sense of minus k cap. Remember, x y is shown like this, therefore, the z axis is coming out of the plane of the screen. Therefore, k cap is coming out of the plane of the screen, and with this theta, if this is omega of the frame, then it is in negative k cap direction. Therefore, my omega vector is theta dot is its magnitude, but now directed in minus k cap direction. Therefore, this is my omega which I have used here, and x vector is x I cap, the capital X, which is this location times I cap. Once you do this rearrangement, then on the right hand side I have this, along the I cap direction I have V e plus capital X dot, and along the j cap I have minus theta dot x, the x coordinate. Now, comparing the two sides, I can obtain, say x, this is from the I cap equation, I cap, and here is this I cap. V e, velocity of the eagle, plus x dot, capital X dot must be V m cosine theta. Therefore, x dot is V m cosine theta minus V e. If I integrate this equation, so this gives me a relation between the velocities. So, relative velocity is x dot, capital X dot, remember. If I integrate this equation, then I expect to find out capital X. Now, why do I want to find this? Because once this eagle has caught the mouse, x has gone to 0. Therefore, if at time capital T eagle has caught the mouse, then capital X at capital time t at time equal to capital T must be 0. That is what I have written here. I integrate this equation over 0 when the eagle just saw the mouse to capital T when it has caught the mouse. When it has caught the mouse, capital X at capital T is 0, and this is the starting, at the start what is this x, that I can find out in terms of h and d. On the right hand side, I have this integral, V e is a constant, therefore, that integration is easy to do. but I have this cosine sitting inside the integral and cosine of theta sitting inside the integral, and the variation of theta is not known to me. Let me keep it as it is. I have used this x 0, remember x 0 is this length x at time t equal to 0 when the eagle has just seen the mouse, and that must be equal to under root of h square plus d square. Once you do this algebra, you will get this integral of cosine theta over 0 to t, which is not known as yet, but one side, the left hand side is completely known. Let us see if we can find out this integral from another approach. That is what we are going to do next. This is the first equation that we have just now derived. Now, let us look at this horizontal direction. I have shown this unit vector in the horizontal direction, eta cap. This is a unit vector in the horizontal direction, which I can always represent in I cap j cap in the x y z coordinates. This is that representation, cosine theta I cap plus sine theta j cap, and I will try to find out what is the horizontal gap. So, right now at time t equal to 0, the horizontal gap is d, but as the eagle flies somewhere here and the mouse goes here, this is the horizontal gap is going to change, it is going to reduce, and when the eagle has caught the mouse, the horizontal gap will also vanish. So, with that idea, I find out this rate of change of horizontal gap, which is xi h dot. I represent that horizontal gap as xi h, and xi h dot is the rate of change of that horizontal gap, which must be equal to this relative velocity of the mouse with respect to the eagle, which we have just now discussed, dot eta cap. This is the relative velocity of the mouse with respect to the eagle, dot eta cap will give me the rate of change of the horizontal gap. And if I write that now explicitly, remember this is our expression of V m with respect to V mouse with respect to the eagle, which is nothing but velocity of the mouse minus velocity of the eagle. And this was represented in terms of x dot and omega cross, so V rel and omega cross r, omega cross x vector. So, that was in the as represented in the rotating frame, but V mouse with respect to the eagle is V mouse minus V eagle, and that is what I have written out here. Once I take the dot product, it simplifies to V m minus V e cosine theta. Once again you see cosine theta is coming, and that is xi h dot. Therefore, if I integrate over time from 0 to capital T, the horizontal gap at capital T must vanish because it has caught the mouse, and xi at 0 is the starting horizontal gap, which is d, and that is equal to the integral. You can see here V m minus V cosine theta integrated over time. V m is a constant, V e is a constant, therefore, those things will come out of the integration. Only thing that I am left with is integral of cosine theta dt integrated from 0 to t. Now, you compare equation 1 and 2, you have this integral sitting on one side and both, therefore, they must be now equal, and from there I can solve for the time to catch the mouse. So, this was an interesting example application of the kinematics. To summarize, we have looked at relative motion in rotating frames and we have discussed some examples. An interesting example was that of the eagle catching the mouse. With that, I will close this lecture.